this house just failed its electrical inspection.
So in this video, we're going to show you 10 reasons why your house might fail an EICR. We're going to go in depth with our body cams and show you every step of the EICR process. So if you're a homeowner who needs an EICR, you're going to learn exactly how it should be done. Or if you're an electrician who is looking to up your skills when it comes to testing and inspection, this video is for you. Make sure you like and subscribe, and let's get into it.
So step one is explain the process to the customer. For example, we're going to be turning the power off at some point during the day, and we want to make sure that that doesn't cause unnecessary interruption for our client. We're also going to walk through with them everything that we do in the inspection and ask them questions about the installation. For example, where's the main bonding for the water and gas? Where is the boiler and heating controls located? Do you have any outbuildings with power in? Do you have any electrics in the loft? And obviously, where is the consumer unit and meter? And the final thing we want to know is, have there been any problems with the electrics? Does anything trip regularly? Is there anything you're worried about? Have you had any alterations or additions done to the electrical system in the recent past? All of that information will help us to know where to start and where we're going with the inspection, but it also helps the customer to know what to expect from us, when we're going to turn the power off, what we're going to need to check, and if there's anything that they don't want us to access. For example, in this property there's a few sockets that are hidden behind heavy pieces of furniture, and the customer said they prefer for us to not move that, so we'll put that on the limitations, which I'll talk to you about a little bit later. Now, you might be wondering, what is an EICR and when do I need one? Well, an EICR stands for Electrical Installation Condition Report, and it's basically like an MOT for your house electrics. It involves a thorough check, as you'll see throughout this video, of all the electrics in your house, both visual and electrical tests, to make sure that the wiring in your house is safe. Now, when do you need one? Well, every house in the UK needs to have one. It should be done every 10 years, which is why our customer here is getting theirs done, because there's a label on the consumer unit that says it's due. The consumer unit was last tested in 2014, is due in 2024. So if you're not sure if you need one, check your consumer unit. There might be a sticker on there. If there isn't a sticker, then it's probably not been done. And for most houses, it should be done every 10 years. If it's a rental property, a landlord has a legal obligation to have their electrics inspected, and EICR, a satisfactory EICR, issued every 5 years. And to be honest, if you're buying a house or if you're moving into a house, I would always recommend that you get the electrics checked before you move in. Also, for commercial properties, they need to be done even more often. And some properties like thatched houses, etc., it's a requirement from an insurance point of view as well, because of the additional fire risk. So there's loads of reasons why you should get an EICR done regularly. And if you haven't had one done in the recent past and you'd like a quote for one, there's a link below where you can give us your information and we can quickly provide a quote for you. Before we start our first set of checks, let's talk about what tools we need. So first and most important is this. We can pretty much do all of our testing and inspection with this voltage detection device. Only joking. What we really need is one of these. This is a multifunction tester. There are various brands and models out there, but this is the one that we use and it is awesome. This is an R2 long wand lead, and I'll explain how we use that a little bit later in the video. For me, an inspection mirror is another vital piece of kit for our visual inspections. These are jump leads which we use for the R1 and R2 test. Absolutely vital is a decent set of hand tools, some good screwdrivers, and my favourite, a pair of long nose pliers which will enable you to pull out wires easily from the terminals. There are a few nice to haves that are not essential but make life easier and speed up the process, like this electric screwdriver, an inspection light, a head torch, an earth leakage clamp meter, a nice sharp Stanley knife, and the ultimate EICR tool for when you're turning off power is one of these, a power bank like this, Jackery. There's a link in the description where you can get a discount on one of these, and I'll show you how we use that a little bit later. It's also handy to have one of these plug-in testers to identify sockets and which circuit they're on. So the first step of our inspection process is visual inspection, and to do that we need to start at the incoming supply at the meter box. Let's go first person. So we're here at the meter box. This is where our main supply comes in. Let me show you what we need to be looking at here. So we've got a 100 amp main cutout fuse. That's something that we'll note on the report. It is a protective multiple earthed installation, or otherwise known as TNCS. That's where the incoming neutral and earth are combined here. Interesting little fact for you. The little red dot there on the main cutout tells you something. What it tells you is that the supply for this property is on the red phase, or what would now be the brown phase with the new modern colours. So if you see a yellow or a blue dot on a main cutout, you know which phase that installation is on. That's another thing that we need to note on the supply. Now, what I always note as well is this. So it's a single cable coming in. So as far as we're aware, it's not on a looped supply. That's not necessarily important for the EICR, but it's good for us to note anyway, because if we were going to do an EV charger here later, we'd need to know that information. We've got a main isolator switch here, which is rated at 100 amps. This is the meter, which is a smart meter. And it looks like we've got 25mm tails going up to our consumer unit and a 16mm earth. Just a quick visual check on this to note all of those details, and importantly just to check if there's anything obvious that we should be worried about, like exposed conductors, tails pulling out, anything like that. But this one all looks pretty good. Now, a quick note about software. We use Mega Cert Suite and it allows us to attach photos to our EICRs. So what I do at every step of the way is just take a photo. It's really useful then to be able to look back on those photos when you're writing up the report, but also attach them to report so that if there's any observations, the customer can see physical photo evidence of the things that you found and know that you're not just making stuff up. So after the meter box, we go to the consumer unit and we'll take the cover off and have a look. I'll hand you over to Luke for that.
So what we're going to do now is, like Jordan said, we're going to take the board cover off and just have a look inside. So I'm just taking a look at the overall installation. Here it's slightly different, this one. You don't see it too often. The buzz bar is actually on the top here. It's all interlinked. Obviously normally you'd have the buzz bar on the bottom, so just be careful obviously that it's isolated when it's live. So here, this is a good example. Normally, like I say, you have the buzz bar, but you can still check. You can check all the terminations. Also, just have a look around, check there's like no thermal damage or anything like that. There's been no arcing going on. If it's a normal consumer unit, this one's sunken in as you can see. But if it's a normal consumer unit, you can look around the condition of it, check there's no big holes in it, anything like that. So yeah, it's just a good overall look of it.
So I'm just filling out the details of the supply here in the inspection schedule. I'm not going to go too much into depth on how we do the paperwork in this video, but we have made a separate video about that, which I'll leave a link below if you're interested in that. Also, shout out to Sparky Ninja, who's done loads of videos about coding. We will be talking about coding in this video, but if you want extra learning, I'll leave you a video link below for Sparky Ninja's EICR coding webinars as well. Right, Luke, I'm going to check the main bonding conductors at the water and gas pipes, but can you just check for me if you can see any in the consumer unit and what size are they?
Yep, so from here we've got 3 main earthing, where it looks like 1 main earth and then 2 bonding. It looks like you've got a 16, there's 2 slightly more smaller ones, which are 2 10s. So yeah, possibly both of those should be earthed.
Great, let's go and have a look. So normally the main bonding to the water is under the sink, and here that is exactly where it is. So we've got our main bonding, we've got our main stopcock to the water now. Interestingly, it is actually a plastic incomer. I don't know if you can see that behind there, but we'll get a little shot of it. There's a blue alkathene pipe. So technically, because the incoming water is plastic, it doesn't actually need bonding. However, it has been done anyway. And there is sometimes a little bit of a debate about actually if the internal pipework is copper, then potentially it could bring in earth potential from somewhere else anyway. So it's worth doing. If there was a plastic insert in this pipe, then there would definitely be no point in bonding it. But in this case, it's done. You can see this 10mm bonding cable coming in, which is what Luke saw in the consumer unit. It loops from this pipe across to this pipe. Now, technically, if I was to be really picky, that bonding clamp should actually be here. It should be within a certain distance from the main stopcock. I think it's within 600mm, is it, or 900mm? We'll double check that. But it should be within, I think, 900mm of the main stopcock, and it should be before any joins. So technically it should be there. But, you know, it is bonded, all these pipes are joining together, and anyway, technically it doesn't really need to be done. So I'm not going to put that down as an observation even. So this leads us to our first reason your house might fail an electrical inspection. It's one that we come across commonly, is lack of main bonding to the incoming services that should be bonded. Normally that's water, gas, and maybe oil if you do have an oil supply to your property. If there is no bonding at all, and there needs to be because it is an incoming metal supply that could bring earth potential into the building, that would go down as a C2, your EICR would be a fail.
So what we're going to do as well on the gas, we're going to do pretty much exactly the same as Jordan. And here I can actually see it coming on the side. So if I open up the cupboard, yep, so it's exactly the same. It's bonded, it's nice and secure in there. It's also got that nice blue tag saying do not remove. So yeah, it's all good.
Now obviously this is just a visual inspection at this point. We will do electrical tests on the continuity of those bonding conductors later on in the video. But right now what I'm going to do is just run around the house, have a visual check of everything that I can see that's electrical, make sure that there are no immediate items of concern that we need to dig into a little bit more when we do the testing process. So we'll have a little check in the bathroom. Now what we're looking for in here is, do we have any shaver sockets? We've got a fan up there, so we're looking at, okay, the fan, does it have an isolator? Does it need an isolator? Thinking about that. We're thinking about the lights in the bathroom. Are they IP rated? Do they need to be? We're also thinking about the measurements of stuff. So there are zones in the bathroom that we need to make sure that certain items of electrical equipment are not within those zones. So here we've got the ceiling height is 237, but I think outside the zone is above 2.2 meters. So we should be all right that those lights are outside of the zones anyway. Anything obviously electrical within that zone would potentially be a no-no. That's what we call zone 0. Then there is zone 1, which extends horizontally up from the bath straight up and across at 2.2 meters. Then outside is zone 2, that extends I think 600. It extends around the bath. So you can visualize this zone and what electrical equipment is allowed or not allowed within that. Now we've got a shaver socket as well, so we want to check that that is compliant. That is a SELV, separated extra low voltage transformer in there, so we'll take note of that. The fan, as I said, whether it's main voltage or low voltage, we'll have a look. And is there a fan isolator on the outside? There is, so we can check that and make sure that that works. We're going to check the immersion heater cupboard and have a look to see if we've got an immersion heater circuit, which we do in this particular case. We'll have a look at the isolator switch for that. Is that compliant? How everything's been wired in here. There are some loose cables, so that might be something that we mention on the report, the fact that there are some unsecured cables that should really be clipped up or put in trunking. We'll also check, if we can, the actual immersion heater element. Looks like we're not going to be able to access that in this particular tank, but often you have a cover which goes over the immersion heater element, and that's got a thermostat in it. That should be what we call a double thermostat, so it has a backup thermal cutout in it. If it doesn't, then that's something that we need to note on the report, especially if there's a plastic tank up in the loft, and I'll explain why in a moment. So the other thing we're going to check is the smoke alarms, make sure they actually work, which they do, and they're interlinked, but we want to check the date on those as well, because to me they look like they might be out of date. In general, smoke alarms have about a 10-year validity, and they always have an expiry date on them, so we want to check to make sure that they're in date, or if they've expired, then we'll note that down on the report. Right, a couple of things of concern here. There is this plug here, which is a bit of 2.5 twin and earth that is wired off a Tesco plug. First of all, as soon as I see a Tesco plug, I think DIY disaster. Somebody's been doing their own electrics here, and I just don't know what it is. You know, what is it powering? I thought it might be powering this spur or something for the central heating. Maybe it's a heating engineer bodge job. You might have seen the crazy shocking video where I actually had a boiler that was wired off a plug like this and the pins were live. That is so dangerous. So this is live, right? I could, if I lick that, I'd be a goner. So I'm not going to touch those pins. That worries me slightly, but I don't know where that goes. So that's one thing. Also, outside here, I've just noticed there is a little metal conduit box there with a armoured cable coming out of it, or what looks like an armoured gland going into it. So we'll check that. I've got a feeling that might be something to do with the power to the outbuilding, but the question is, where is it wired from? Is it wired from a socket on the inside? Is it that twin and earth maybe? But I doubt it somehow. We need to investigate that and check that box to make sure that there's no water and damage inside that. Right, we've done a bit further digging on this, and we found that the one saying washing machine here, when we turn that off, actually turns this freezer off. So I think there used to be a washing machine here, they've removed it and put the freezer in, and then they've actually wired a socket under the cupboard here. Oh wait, no, it's slightly different. So there's a double socket here, which, let's have a look. Turn that washing machine on, then if we unplug this, what happens? That stays on. Okay, so that is maybe wired off the washing machine circuit still? Yeah, okay, right, so what happens then? That washing machine is actually powering this socket. So it's powering the washing machine here, and it's powering the freezer. But then there's another single socket at the back there, which has got that twin and earth going into it. That is off this plug here, and that does this. So if we turn that on, then we unplug our plug, there's no power to this. So it's a little bit of a Heath Robinson way of doing it. However, it's not overloaded at least. There is only this appliance on it and there's only a single socket. We'll definitely note it on the report, but I don't think it necessarily warrants a C2, but it's probably a C3.
Hey guys, so quick note here about what the codes mean. C1, very bad juju. What it means is big problems, not just potential danger, but actual real danger, live parts exposed, things like that. C1s are the kind of stuff that we electricians have to rectify immediately, otherwise somebody could get seriously hurt. C2 is potentially dangerous. So what it means is there's not an immediate danger there now, but if one other thing went wrong, it could cause danger to somebody. So it does cause an unsatisfactory result on the EICR, but it's not as serious as a C1. C3 is improvement recommended. What that means is it's not necessarily dangerous or potentially dangerous, but it doesn't comply, and we would recommend that it gets improved. There's also FI, which stands for further investigation. What that means is we need to do some further investigation at another date in order to find out more about this particular situation, as we haven't had time to do it during the EICR. That results in an unsatisfactory result as well, so it's something that should only be put down if there's a serious problem that needs to be investigated that you don't have time for on the day. You can also note other observations that aren't necessarily codable, so that explains the coding. Back to the video.
So now that our visual inspection is done, we've got a good overview of how everything looks and anything that might be glaringly obvious we've already picked up and made a note of. We're going to start with our actual test sequence. Now let me know in the comments how you do the test sequence on an EICR. There is an official prescribed way that you're supposed to do it for what's called initial verification, which is where you're actually doing the initial testing on a brand new installation. That usually goes dead tests, and then you go over to your live tests, then your phase sequence if it's a 3-phase installation, and then finally your RCD tests. Now we could follow that test sequence on an EICR, however it's a bit faffy because if you've got to disconnect your conductors to do your R1 and R2s, then reconnect them, then disconnect them again for the insulation resistance and stuff, is a bit faffy. So what I tend to do is this: I do my ZE and PFC, then I do my long wander lead test where we run around and check our continuity of all the various points, and then I go circuit by circuit, do R1 and R2, insulation resistance, and then we've got a choice about whether we calculate our ZS or we measure it, and we'll talk about that in a bit. So we're going to start with our ZE, in this case our external earth fault loop impedance test. I'm just getting my tester set up. Now this is a 2-lead test, and with the Mega you've got this nice probe that's actually got a button on it. So for our external earth fault loop impedance test, we have to do a couple of things. We have to disconnect our bonding conductors, because we don't want any parallel paths to reflect in our readings. So the best way I find to do this, to be honest, is just to disconnect the main earth and just test the main earth. But to do that safely, we're going to need to just turn the main switch off because we don't want anything to be live while we've got no main earth. So what I'll do is just turn all the breakers off, turn the main switch off, and then disconnect the main earth conductor, which is, I think, the one on the far right here.
Right, so we've got 0.24 ohms. Now, the question is that acceptable or not? Because we're on a TNCS system or a PME, 0.24 is absolutely fine. It's less than the 0.35 maximum required. So we'll write that down on our report. So once we've done our ZE or external earth fault loop impedance test, which is basically measuring the resistance of the cables back to the transformer, we connect our main earth back into the board now before we do our PFC and PSCC, which is prospective fault current and prospective short circuit current. We connect that back in, we turn everything back on, and then we do those tests with everything connected. And we test then between our earth bar with all the earths connected and our live terminal. And the figure that we want is here at the top, 1.02 Ka or kiloamps. Basically, this test reveals the maximum amount of current that can flow in the event of a fault. So imagine there was a direct short between the line conductor here and the earth bar. If those were banged together, what would happen is a huge amount of current would flow, and that current would only be limited by the resistance of the cables essentially, or by that ZE reading that we've got. So with a ZE reading of that, we have a maximum current flow of 1.02 kiloamps or 1000 amps is what would flow in the event of a fault. And that is why these breakers have a rating on them of the maximum short circuit current that they can withstand in the event of a fault. So we need to check basically that these breakers are rated to above the short circuit or fault current reading that we've got. So we've just done our PEFC, our prospective earth fault current. Now we're going to do our prospective short circuit current, which is between line and neutral, and we just do that here at the main switch. So I'm going to change the setting on the tester here to line or line to neutral. Press test. Right, so we've got 920 amps. So that is our maximum PSCC, prospective short circuit current, and we can write those down on our report.
Hey guys, I've got a little secret for you. We're in the studio now filming some Tools for Sparks videos. But in other news, Tradify have just released forms. Forms enable you to complete EICRs, minor work certificates, landlords, gas safety certificates, boiler service records, and loads of other important forms in Tradify, which means you don't need another software platform to deal with your paperwork. Tradify has it all. If you haven't used Tradify yet, it's really worth checking out if you want to get organised for your business. You can do so with a 50% discount for your first 3 months using our special code, which is in the description below. And if you want to just try it out, there's a no obligation, free 14-day trial with no credit card details needed. Thanks to Tradify for sponsoring today's video. So while I continue filling out a few bits on the report and adding some photos, Luke is going to take you around and do the R2 long wander lead test.
What I'm going to do now is the R2 wander lead testing, and basically that's just going around every fixture and fitting within the house, anything metal, just to check that it's got an earth going to it. So what we do is we put this cock clip onto the main earth terminal bar, and then we'll go around using a probe and you just dab it on everything metal just to check that it's got an earth reading. It'll give you a reading on the tester. So what we'll do first, just a little tip, sometimes people forget, is you've just got to null the leads, and basically that means it's going to get rid of the resistance because it's a 50-metre cable on this little drum. So we'll get rid of the resistance on this cable so you get a proper reading. So that there's the reading of the resistance of the cable. So if we push it, and then it brings it back to 0. So basically that's got rid of the resistance of this. So within this property, most of the fittings and fixtures, as you can see, the switches and sockets, they are all actually plastic. Just not getting a reading in there. So we'll note that down. Brilliant. So everything, yeah, apart from a couple of little things, we'll have a bit of more of a look into them. Everything seems to have an earth.
So this brings us to our second point that could fail your house EICR, is metal light fittings that aren't earthed. If we find during the R2 wander lead test, like Luke's just done, that there is no earth to a light fitting like this, it will be noted as a C2, potentially dangerous. And the reason is, if a live wire pulled out of the back of the light fitting and touched the casing, if it wasn't earthed, it wouldn't trip the breaker. You could touch that light fitting and get an electric shock. So that is one vital thing that we always check, is to make sure any metal lights are earthed.
So while we've got the wand lead out, we're actually going to do the testing of the main protective bonding. So first things first is we need to take them out of the board, and then I'll show you from there. So these are actually unlabelled. So what we'll do is we'll take them both out, and then we'll find and see which one goes to what.
So in the past, I used to get called out for not disconnecting the main bonding conductor at both ends when doing a long wand lead test for the main bonding. And it's complete nonsense. You don't need to disconnect it at both ends, you only need to disconnect it at one. Let me explain. So imagine your connection in your board is here, 10mm earth going to your pipe. Here's your connection to your pipe. Then here is your pipe work all going all over the place. This is your actual main earthing connection. Imagine this is the boiler or something. So the boiler is also connected back via a separate earth to the earth bar. So the reason you would disconnect the main bonding from the earth bar is because if you don't, those are connected together, you get parallel paths. So your reading would go this way and that way through the boiler, etc. And it would lower your reading because resistance in parallel divides. However, if you disconnect it from the main terminal in the board, you're only testing this way. There's no possibility for parallel paths. So you are testing from here to here. There is no way that the resistance can go parallel any other way. So you're getting a clear reading that way. You don't need to disconnect it at both ends. You could do. You're doing the same thing basically, and it doesn't make any difference. So let me know in the comments if I'm wrong, but I'm pretty sure that's right.
As I showed you, I've disconnected that end. So what we're going to do is we're going to put it on here now, this earth bonding, and just see if we get the reading. What is that getting a reading of? So that got a reading here as well.
You will get a reading.
But you're getting reading on both, so somehow they are joining somehow, do you know what I mean?
So we did just find something interesting, which is that if you only disconnect them at the board, but not at the bonding clamp end, you can, for example, get a false reading if you're testing the gas, but you're actually clamped onto the water bonding cable, because the gas pipe goes into the boiler, the water pipe goes into the boiler, and ultimately you will get a reading through the water pipe into the gas pipe when you test it at that end. So actually it's kind of right that you should disconnect them at both ends if you want an exact reading and know which bonding cable is which, but for the purposes of continuity and just checking that main conductor going across is continuous is not necessary, but it might be good practice to do anyway. So now that we've done kind of a global earth continuity test on any exposed metalwork throughout the property, that gives us a good view that most of the metallic fittings that need to be earthed are earthed. However, what we need to do is an R1 and R2 test on every individual circuit, ideally at the furthest point, so that we can make sure that there is continuity of earth going, or continuity of CPC is the official term, going to the furthest point on each circuit and back. So we'll start that on the cooker circuit, and this is a dead test, so we need to turn the circuit off in order to do that. We'll take the cover off and we'll link out the line and CPC there and do a test back at board. So with your R1 and R2 testing, you've got a bit of a choice of where you do it. You can either do it at the board or here, but either way you need to link the line and the CPC together. So I kind of tend to choose whichever place is easier to do that link, and I use these in order to do that. The only thing you've got to be careful of though is to make sure that you are actually linking out the right circuit, because imagine I've turned the breaker off for this, but actually I've chosen the wrong breaker and this is still live. If I put a link here between line and CPC now, there's going to be a massive explosion. So a quick voltage test is a good safe thing to do, just to make sure that you have actually turned the right circuit off. You can do it with this or a GS38 pair of test leads, obviously. I want to choose the incoming line, which is in the top in this case, so it's easy enough for me to disconnect. So we'll do that here, and then I'll connect my little jump leads on there. So I've now linked the line and CPC, and we'll do a continuity test at the consumer unit. So for this test we need to put our tester onto the low resistant ohms reading. We've removed the resistance of the leads. Now we'll test between the line outgoing on the breaker and the earth bar here. Now we've got two earth bars, so we just need to be a bit careful of that. This is the non-RCD side, which is the one that we should be testing. This is the RCD side, which will get a different reading if we test on that side. So we're going to test here, and we've got 0.22 Now, you might wonder, how do I know whether that reading is correct or good or not? The way that you know is by actually calculating what it should be roughly based on the size of the cable and the length of the cable. So in this case, it looks like it's a 10 mil, I believe, going over there. It's on a 32 amp breaker, but yeah, I'm pretty sure it's a 10 mil. It's quite big. And it's probably 15 meters of cable. So we can do a little calculation and see if it's about right.
So to calculate the expected resistance, we take our cable resistance per meter, which is in the tables for the cable design. We times that by the length of the cable, and that will give us the expected resistance reading that we should get. For example, a 10 millimeter squared twin and CPC cable has a 10 millimeter squared line conductor, which has a resistance per meter of 1.83 milliohms, and a 4mm squared CPC conductor, which has 4.61 milliohms per meter of resistance. So we add those together and we get 6.44 milliohms per meter. So we take 6.44, we multiply that by the length of the cable, say 20 meters, and that would give us 128.8 milliohms or 0.128 ohms of expected R1 and R2 for a cable of that length. Or we can back calculate the length by calculating the resistance measured times 1000. We divide that by our milliohms per meter figure for the cable. For example, we could take our R1 and R2 reading of 0.2 ohms, times that by 1000, divide it by 6.44, which is the milliohms per meter of the cable, and that gives us a cable length of 31 meters.
So I'm happy with 0.2 for that length of circuit. I think that's fine. So a couple of things that we note on the visual inspection on the board that aren't quite right is the breaker here. They've used a chint breaker in a square D board, so it's not necessarily type tested for the board. Now it does fit, it looks okay. In fact, chint is probably just a rebranded version of the square D breaker. I know that Schneider also owns square D now, so you might find the same breakers labelled as Schneider or Merlin-Gerin, as they say in French, but the point is it's a different brand, so we'll just note it down as a C3, but it's not a major issue. Other things, obviously there's no RCD protection on these 5 circuits here, so potentially they would need RCD protection, and we'll talk about why later on in the video, but that's definitely something for us to note. So when it comes to doing the R1 and R2 testing on the lights, again we try and find the furthest point. Sometimes it's a pendant, sometimes it's a downlight. On the ground floor here, we're kind of the furthest corner from the building, so I'm going to pick one of these downlights here, and to be honest, some of them look like they've been out, so they're not like painted in. Others, they're painted in and they're really hard to get out without damaging the ceiling, so we have to be reasonable about it. But it looks like this one has come down before, so we do a sampling anyway. We have to remove a certain number of accessories for visual inspection, and that includes downlights. And to be honest, one of the classic fails that we have when it comes to this kind of test and just checking the downlights in general is that they're not wired up properly, just like that. So this is another reason you might fail an EICR is, all of these single insulated conductors are showing. They've just wired these GU10 downlights into this tiny little thing here, and rather than using a proper junction box to enclose these connections, they've just tried to shove them all into the tiny little connector blocks that come with the downlight. It's just basically impossible to do it properly. Whether it's a C2 or a C3, I'll let you guys debate that in the comments, but what I'm going to do is just check a few others, and if we can find an end of line, then we will, and we'll get our R1 and R2 test there. Try not to get your fingers trapped under these. Okay, yeah, so this one, they've just wired it in 2-core flex. There's no earth even going to it, I should imagine. So although this little bit of metal here technically needs an earth, this is 2-core flex. I know that because that's literally wired off this one. Oh, actually there's a tiny little earth in there. So we'll get our tester and we'll do R1 and R2 test. This is how rubbish the design is on these downlights. They've just taped it up with sellotape because the case just kept dropping off. I mean, nowadays we install these really good quality downlights that have got integrated connections in a nice push fit connection box, and it's much better. These things are just really difficult to do properly, and often they're sort of done by builders or DIYers and they're never quite wired up properly. So we often find failures when it comes to these downlight installations. That's weird. Okay, so that's a good example, right? So I've just done the test here and I'm like, oh, why is there no reading? Well, there's no reading probably because the switch is turned off. And this is the whole advantage of doing R1 and R2 testing. If we turn the switch on, we know that we're switching the line conductor and not the neutral. So we're actually doing a polarity test at the same time. Okay, got no reading still. So unless there is literally no continuity, try the switch again, just in case I was doing the wrong switch. Classic. So I'm gonna have to investigate this a little bit further. Right, and here we go. So again, we've got a 2-core flex. They've not even connected the earth on this one. It's literally just loose. So that one goes to here. I've got a feeling that there might be some kind of junction box above here or something where they've joined multiple. Oh yeah. Yeah. The plot thickens. So this is where having a decent knife comes in handy, because sometimes accessories are painted in or plastered in and you've got to kind of score around them to remove them. So often switches, sockets, they're painted in. Rather than just ripping them off the wall and ripping half the paint with you, if you score neatly around the edge with a very sharp knife like this, you can remove them neatly. So that's what I'm going to do with this, just being very careful to not get my hands in the way. And by the way, Unilite are one of our supporters of our channel and we're able to give great discounts on their products. So their lights, their knives, all of that stuff, you can get a really good discount using a special code that you'll find in the description of this video. So I've scored around that now and that will nice and smoothly come out. Yeah, so again, they've just done the whole in and out with the flex thing, but they've not actually connected the earth here either. So they've just cut all the earths off. We see this so often. But here is a junction box. And here we have twin and earth cables. So hopefully we've got an earth in there and we can at least get an R1 and R2 reading from that point there. Oof. 69 kilo ohms. So basically we've got a very loose earth there somewhere. That is way too high. So even the earth within this junction box somehow is not connected properly wherever it comes from. So this is the point now where you're like, okay, do we do some further investigation? Do we just note it down and we're going to have to investigate it later? Essentially, I feel like we're just going to end up having to take all of these downlights down. There is one there that looks like it might have been removed before, so I might just check that one. But I don't want to have to score around and cut every single one out. So I'm going to just check 1 or 2 more. And if we've not got a good reading at any of them, then we're going to have to look at sorting them all out as part of the remedial work. So this one, what the heck?
Oh, there's another one.
They've run like a 3-core.
Junction.
Yeah. Oh no, look. Oh my goodness.
What?
I mean, basically this is just screaming like DIY or builders. Just flick the switch for me. Just in case. In case it's high resistance going through the switch. No. Oh. There we go. Right. It's because the switch wasn't on. So, there's a lesson. So, the switch, we were getting a small amount of resistance through the switch. So, for some reason, the switch was not completely isolating it. Now we've got 0.79. So, we do actually have earth continuity. So, we do have a good reading on the hard wiring to the junction boxes, but we don't have any continuity to the actual metal part of the fitting, which technically that should be clipped onto there, and it should earth this whole metallic part of the light because it's a mains voltage light, GU10. That is part of the design of the light fitting. Often now downlights we wire are just class 2, which means they don't need an earth, but in these cases these ones are definitely class 1 and they definitely need an earth, so we're going to have to note that down. So we should also note that these are not fire rated, these downlights, and they should be because there is a habitable space up above. They should be designed to maintain the fire barrier of the ceiling so that if there's a fire, basically the fire doesn't spread up through these downlight holes. So what I'm going to do is recommend to the client that we put in new downlights that are fire rated, proper integrated LED downlights. They'll give a much better light in here anyway, and it'll just smarten the whole lot up. And also it'll mean that they're fire rated and the fire barrier of the ceiling is maintained.
We're just moving on to the smoke detector circuit now. It's actually only 2 in the property. It's 1 downstairs in the hallway and then 1 up here on the landing. So it's always good. I think Jordan did mention it. When you take them down, try and look for a date on them. There's a date there. It says December the 30th, 2023. So yeah, we'll note that down there in the EICR report that they could do with changing. Testing smoke alarms is literally just the same as a lighting circuit. You've just got to find the end of line and then check you've got an R1, R2 at it. There we go. I've got a reading of 0.75. And it's always good as well, just to test them while you're here, and also if they're interlinking, test that they're all linking properly as well.
So it's time for lunch, and Luke's warming up his lunch with the heated lunchbox, which is running off the Jackery. But we also use this to run the customer's Wi-Fi when we are turning off the socket circuit, which we'll be doing straight after lunch. We can plug their Wi-Fi router into this, and we can even charge our batteries and stuff. We can run the laptop off of it. So it's really, really handy for doing EICRs when you're turning power on and off quite a lot. If you want to find out more, we do have a special discount code in the description where you can get one of these.
So another reason you might fail the EICR during the visual inspection is if there's no RCD protection for the circuits that need it. Now in this case we do have an RCD. RCD stands for residual current device. It basically measures earth leakage to circuits, and if there's excessive earth leakage it will trip. That's protection against electric shock and burns, which is really important. Now in this case the RCD is just protecting the socket circuits, and that's good because RCDs are definitely needed for sockets. However, nowadays really you should have RCD protection on everything, particularly lights in bathrooms. It's important to have RCD protection on, and in this case we don't have RCD protection for the lights in the bathroom, so that would be a fail in this case. Other things that need RCD protection are any lights at all now according to the latest regulations, but we wouldn't necessarily fail it on that because when it was designed it was okay. Also, cables buried in walls need RCD protection so that if you drill or screw through a cable in a wall it's not going to kill you. So in general now we fit all RCPO consumer units where every circuit has its own individual RCD protection. However, this is probably what we'd call a 16th edition consumer unit where half of the loads have RCD protection and half don't. So we will note it as a C2 that there's no RCD protection for the lights, because that is definitely a fail in this case.
So we've got to wade across this loft to check the the solar setup. Oh my goodness, I just noticed that. Okay, that's definitely not great. What the heck is that? Look, that is really weird. The plot thickens. So we've got some kind of weird light extension socket thing here. The question is it part of the fixed wiring or not? So if you think about this is all off that. Technically that's not fixed wiring, but it's still a bodge. And then obviously this part is fixed wiring. You get this thing where you're like, right, this is dodgy, but is it part of the fixed wiring? Not really. So does it come under the inspection report? Technically no, but I'm still going to note it down anyway because it's not right and it's not safe. Anyway, solar. So we're going to wade across this loft now. I'm being careful where I walk here. I know that there are joists here on the floor, which is why I'm walking in this part. The other way you can do it is obviously make sure you walk in line with these posts here, because you know that there's going to be joists going across there and there. I'm going to take a picture of this solar stuff and then I'm just going to have a look. 100 amp, 100 milliamp RCD in there. So it looks like the feed from our consumer unit is this 2.5 twin and earth here. Goes into this RCD because there's no RCD protection in the board, and obviously the inverter probably needs RCD. So I'll take a picture of that and add that as another RCD that we need to test in the system. Then we've got our AC isolator. Then we've got a generation meter. Then we've got another AC isolator here. Then that goes out in flex into this inverter. Check that DC isolator. That seems to work okay. But what I'm not sure about is this. So this twin and earth here seems to be going out of the inverter. I've got a feeling that the customer has tried to run his immersion heater off of this. It's all just slung in, this twin and earth. It's just all loose. It should be clipped up properly at least. The DC cables should have danger notice on, saying danger live when daylight. We are going to be fitting battery storage here later, so it's always good to have a record of the existing inverter so that we know what we're dealing with when it comes to fitting the battery storage. Some shocking discoveries up there. Okay, so we found where that twin earth goes from the inverter. It goes into this. Goodness knows what this is. There's obviously some kind of feed, permanent feed, coming from the inverter. And then this is like a switched feed, so that when the inverter is outputting above a certain amount, it powers this auxiliary contactor, which activates this contactor. And then the contactor sends power to the immersion heater to kick the immersion heater on and heat the hot water. This is basically like a bit of a DIY sort of Heath Robinson attempt at doing an eddy. Definitely that's going to go on the report. Not great really, to be honest, but let me know what your thoughts are in the comments. I mean, I say DIY, but it's quite possible that the original solar installers did this. Nothing surprises me anymore when it comes to solar, to be honest. Right, so trying to test this solar circuit, R1 and R2. Luke's linked it out. I have, smacked my head on the inverter. Nice. I was testing it here, but it was tripping the RCD every time, bizarrely, because there's no power, but I guess just the small amount of power from the tester would do that. Yep, okay, we've got 0.24. So that's good. Disconnect the link and then liven it up, and I'll do an RCD test on this RCD while I'm still up here. The router, etc., is all wired off a plug in the kitchen, and as we're about to turn the socket circuits off, what we want to do for our own sake, in this case, customer's not in, but we're going to plug the Wi-Fi router into the Jackery so that that's working constantly, even when we turn the sockets off, so that I can still get an internet connection for the laptop as we're filling out the certificate online. There we go. My head torch battery ran out as well, So now we come to the next step, which is our ring continuity tests. Basically in the UK we have this weird thing called the ring circuit, which you either love or you hate depending on how old you are. I hate them. I think they're stupid, pointless. It's a remnant from the war.
Listen, don't mention the war.
When there was a copper shortage, and you could basically get a higher ampage on a circuit by running two smaller cables rather than one big cable. That is, I think, where it comes from. But essentially, you've got two cables running round in a ring, going from socket to socket and then back to the consumer unit. And we've got to make sure that it's continuous, because with a 2.5mm squared conductor, we can install a 32 amp breaker. And then what we do, the first test on the ring continuity test is what we call the end-to-end test. So we literally take the two wires out of the breaker, we clip our croc clips on like this, and then what we're looking for is a low ohms reading. So here we've got 0.4 ohms from end to end, which is fantastic. So we'll do the same on the neutrals, and because the neutrals are both 2.5 mil as well, we should have the same reading roughly. Sometimes I just squeeze it onto the thing and the reading will get even better. But there we go, we've got 0.42 there, 41, slightly higher, but within any kind of tolerances, so that's fine. And then the CPCs are actually 1.5mm squared, so we will expect a higher reading on those, which we do have, 0.66, which is absolutely fine. So that's our end-to-ends, and we're all good on those. Now, this is another area where your EICR would be a fail if you have a broken ring circuit on the line or neutral conductor. What happens sometimes is a wire pulls out of the back of a socket. Over time it gets loose, or somebody does some alterations and basically the whole thing isn't done properly and there's a break in the ring. That means that all of the power will be going down one side of the circuit only on a 2.5mm conductor, and it can actually overload that conductor, overheat and cause fires, which is why I'm not a fan of the ring circuit, because there's just too much that can go wrong. We come across a lot of broken ring circuits on EICRs, so that's another reason why your house might fail an EICR. So sometimes you can't actually figure out which ends are which in the consumer unit. Like in this case, we can't see the cables coming into the consumer unit because they've stripped them back too far. So it's easier to do the R1 and R2 crossover figure of 8 test at a socket, and Luke's going to show you how to do that.
So what we have here is one leg here and one leg here, and all we do is cross the CPC with the opposite leg, the line on that, and the same again on the other side. So we have the CPC of this leg, and we link it with the opposite leg, the line on that. We will just test both legs. We'll just do exactly the same as what we did downstairs and walk around each socket on that circuit and record the highest. So for the second test, we're going to do the figure of 8 test, which is basically R1, R2. And that involves basically getting the line and the earth opposite. So you have the line out of one leg and the earth out of the opposite leg, and basically just crisscross them. So I'll show you what I mean here. So if I show you here, I've got the line off this leg with the opposite earth of the other leg. So what I'm going to do now is I'm going to test the continuity on each leg. So if I know my leads again just quickly, I'll take it on one leg there and the other leg there, and that will give me my R1, R2 reading. So what I'll do now is I'll go around each socket which is on that circuit and plug in, and then from there I'll record the highest. Because it's just a 2-lead test, you just need to have your line and your CPC, and then from here we'll go around each socket and, like I say, record the highest.
Right, so now that Luke's done the R1 and R2 on that ring circuit, before we put all of the conductors back in the breakers, we want to do insulation resistance test. Now what that is basically where we push a load of voltage into the circuit to check that there's no kind of leakage across between the conductors. It's basically checking that the insulation of the conductors in the circuit is sound and there's no potential low resistances between. So between the line and the neutral, the line and the earth or CPC, and the neutral and CPC, there should be no connection. There should be a high resistance over a certain level of mega ohms. So we do a test. We can either do it at 500 volts or 250 volts. I prefer to do it at 250 at least to start with, just in case there's any sensitive electronic devices connected, because if we push 500 volts into the circuit and something's connected that we didn't know about, we could blow it up. And what we've done here is we just put the croc clip, the link wire here between the line and the neutral, so then we can test from those to the CPCs first of all. So we're basically testing between line and CPC and neutral and CPC at the same time, and we press our test button and we should have a high level of resistance. In this case, perfect, we've got 999 mega ohms, which is excellent. Now if it was below 2 mega ohms, that would be a fail, or at least we would require further investigation, because what could be the case is that some broken down insulation in the circuit, or there could be a screw that's slightly going through the wire in the back of a box or something like that. We often find little faults like that where you take the cover off and the screw from the socket has gone into the live wire at the side and it's shorted out. This is again why it's good to have RCD protection, because if you've got an RCD, it will usually trip if there's a very low level of insulation resistance. So once we've done between line and neutral and CPC, we can also do between line and neutral separately. We've unplugged everything from the sockets. I think we've switched off all the switch fuse connection units and stuff. So if we press test now, yeah, see, this is what a low reading would look like. So we've got a 0.3. We've got below 2 mega ohms anyway, which to be honest just probably means that there's something still connected on the circuit. There might be something spurring off that we've not switched off, or anything like that. So I'm not too worried about that, and we usually just put the line to neutral down as a limitation, because it's almost impossible to disconnect all the loads in reality on these kind of testing and inspection jobs. So we're all clear on that one for insulation resistance. We will talk about how we do a global insulation resistance test across everything once we've buttoned up this circuit. So I'm just preparing the ground floor socket circuit, and something that I want to talk to you about is these.
These are supposed to be a safety device, but they're really not, because British standard socket outlets are built to very stringent regulations, which means that when you push that earth pin in there, there's shutters here that come up. So if you put that in, it actually opens the shutters, and then these get brittle over time. They can snap off and leave open socket shutters, or they can just damage the springs in the socket because they're not meant to be kept open all the time anyway. So I would not recommend fitting these. British sockets are perfectly safe without them. Just taking the cover off this, and this old Bosch electric screwdriver is extremely handy when you're doing EICRs, just for quickly taking socket covers off. And as with all the tools that we're talking about in today's video, there will be links in the description where you can get them, and if you do buy them through our links, it does help support the channel as well. We'll do a ring continuity test on this circuit. Right, little top tip here. When you take these socket faces off, it's so easy to lose these screws if you just put them down. So what I do is I put them through the opposite way, through the lugs. That just means that they don't get lost or fall out anywhere awkward. And also take the one from that side and keep it on that side, because sometimes they cross thread themselves a little bit, and if you try and put that one into that side, it won't fit and it will ruin the lug. And if you're a customer, please, 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 I beg you, do not get the sockets with these little inserts. They are so annoying for electricians to remove later, and I know people think they look nicer and stuff. They don't. Just get nice looking sockets in the first place. So the other little bugbear that I have about people wiring up sockets is when they do this, they twist the wires together. It just makes it really annoying to do the test that we're trying to do here, which is, oh yeah, see, it snaps off anyway. Strip that back a little bit and then re-terminate it properly into the socket, and then I can do the end-to-end as intended on this, like so. Now, in addition to the crossover figure of 8 test on the line and CPC, you can actually do it on the neutral and CPC as well. If you want to go really extra, just make sure that you've got a nice kind of loop with the neutrals. And interestingly, on this, we've got a slightly lower reading on the neutrals than we did on the lines. Right, so the next step we're going to do is insulation resistance on all the circuits. We've obviously done it on our ring circuits already while we had the wires out, but we're going to do a global insulation resistance test now, which basically means we can test multiple circuits at the same time. If the readings are good, which they should be in a fairly new property like this, then we don't actually need to do individual tests. So what we'll do is just turn these breakers off for the non-RCD side, and then we will do a test between line and CPC here, 250 volts, test, and we've got 0. Great. Okay, let's do line to CPC individually. Okay, so some circuits were good, like the second circuit along, which is the immersion heater circuit, we've got greater than 999. Lighting, we've got low, 0. Yeah, so the thing is, because there's connected equipment, what happens is, although your lives are isolated here, it feeds back through the neutral, so you actually just have to disconnect the neutrals one by one, and then you'll get a good reading. So now we disconnected the neutral from our cooker circuit, and then if we test from neutral to CPC now, we should have a fairly high reading. We've got 11.4 mega ohms. That's fine, it's above 2. It's still a little bit low. If we turn the isolator off for the cooker, there you go, so Luke's turned the isolator off for the cooker now, and we've got 999. So what that means is that low-ish reading was reading through the cooker, through all the electronics inside the cooker, maybe the element and stuff like that. So he's turned it on now, and you can see the reading's gone back down. So that's fine. So if you turn it off still, Luke,
yeah,
we'll just do line. We'll just do line to CPC. We've got the same. Turn the isolator off. And there we go, we've got a high reading. So that is basically how we do insulation resistance. We just go circuit by circuit, disconnect the neutral, and then do our tests, and then pop them back in. So our next series of tests is our impedance tests, and those are live tests. So that's where we turn the circuits on and we can test at the furthest point of each circuit and get an earth loop impedance reading, or ZS. Now there's two ways of doing this. You can measure it or you can calculate it. And there's a little common debate that happens sometimes about calculating. You cannot calculate R1 and R2 based on ZS, so you can't do a live test and then work out your R1 and R2 based on that, but you can calculate your ZS based on your R1 and R2 because that's a fixed test. So what we do to calculate ZS, or earth loop impedance, is we take our ZE, which we already took at the start, 0.24, then we add our R1 and R2. So say for example on the socket circuit it was 0.4, we take 0.24 plus 0.4 and that gives us a ZS reading which is calculated of 0.64. Then we check whether that's within the required maximum for the particular circuit breaker that we're on. In most cases we calculate ZS, but I am going to show you how to do an actual ZS test at nearby socket. Okay, so I'm going to do earth loop impedance just to demonstrate at a socket. Now it's perfectly safe to do this, so we can do it. Sometimes it's good practice to do it, although it's really not necessary if you do have an R1 and R2 reading anyway. But we can do it. However, doing live testing at points where you could have exposed live conductors, like a light fitting or a switch or something, is not recommended because you're putting yourself in danger. So in general, it's better to calculate ZS if you can. But this one, all we do is put it on the ZS test setting, and then it does a test, and it gives us 0.55, which is a little bit lower than our calculated version, but that's absolutely fine. And in general, it's just a rough guide to make sure that this is below the maximum required by the regulations in order for the circuit breaker to trip. Simple as that. What we need to do is test this RCD to see if it's working safely or not. Now, just be careful, because I made this mistake earlier. Don't test there, because that's the incoming side on this board. That is the outgoing side. So hopefully I can get a live contact somewhere on the top here. No, it doesn't look like I can. So in this case, I'm going to have to just turn on one of the circuit breakers in order to basically get power coming through. So I'll just do the lighting, because that's not going to cause too many issues. It's better if you can test it without any loads, but lighting shouldn't really cause any problems. So I've set my tester to half times the rated current, which is 30 milliamps, and I press test, and it should not trip, which it doesn't. So then I'll test again at 180 degrees of the sine wave. It should not trip, which it doesn't. Good. So now we set it to 1 times. Just note as well, I'm setting it on the AC setting. You don't need to do the whole type A setting, etc. The regulations state that just testing it on the AC setting is fine. So we test it now there, and we have 18.9 milliseconds. Now it should be at 1 times the rated current. It should trip within 200 milliseconds, so we're well within that. And then we reset it. We change it to 180 degrees of the sine wave again. Press test. 19.9, and we record the highest reading, which is that 19.9 reading. The final test on the RCD, which is very important, is the test button test, which is basically a physical functional test that you should do, and customers should actually be reminded to test these regularly to make sure that they're working, which it is. So our RCD is all good.
Right, so a biggest tip is when you've done your testing, make sure you plug things back in, because you don't really want angry customers ringing you up when you haven't plugged their freezer in and all their food's gone bad. So yeah, that is really important. When you finish, just make sure you go around every single socket and check that it's plugged in.
Okay, so here at the meter box, there's a couple of things that we're going to check. Labelling wise, because the customer's got solar, they should have a label here that is for the fire brigade that says basically warning, solar PV on roof, live during daylight. That's important for the fire brigade to know about. So there isn't one, so we'll note that down on the report, but it's only a C3. The other thing that we're going to do, which is a little bit extra that we like to do at Artisan, is do an earth leakage test using this clamp meter. So what we do is we clamp it round the line and neutral tails at the origin, so that it's measuring the whole installation. We check, and we got a reading here, so we've got 17.6 milliamps of earth leakage. Now our RCD is 30 milliamps, so it means if this is the leakage on all the RCD protected circuits,
It's close to getting to the point where it would actually trip the RCD. However, because we've got multiple circuits that are not on the RCD, this probably includes some earth leakage from those circuits as well. We are planning to fit an all RCBO consumer unit here, which will spread that earth leakage across multiple circuits. And this is quite normal because with this modern age of electronic devices, solar inverters give off a bit of earth leakage, computers, TVs, all of that stuff, they all give off a bit of earth leakage, and what happens is it builds up. I mean, it's up to 25 milliamps now, and it builds up, but it can cause nuisance tripping when you've only got one RCD with all of that earth leakage across it. It can trip the RCD when it's actually perfectly safe, but it's just a build up of too much earth leakage from too many circuits. So we're going to just write this down as a note on the report. It's good for us to know for future reference anyway.
So I'm just finishing up the report now. The customer's given us a nice cup of tea, and there's quite a few things to note on this EICR, a few C2s, a few C3s, but we are going to be back here to do all the remedial work, upgrade the consumer unit, and fit a Tesla Powerwall for the customer. So I hope you've enjoyed this deep dive video on how to do an EICR. Let us know in the comments if there's anything we've missed. Is there any tips and tricks that you'd like to share with our audience? We'd love to continue the conversation in the comments. And why not sit back and watch another of our videos, because we've got quite a few interesting videos in the bank. So you'll see up here on the screen 2 videos that YouTube thinks you might enjoy. But either way, thanks for watching. We'll see you on the next one.